Okay, so today what I wanted to do is start what's probably one of the most important discussions in this class. And it's something that I'll do this week, um, starting today, and probably continue into next week. So what I'm going to be doing is a more detailed study of the one-loop structure of quantum electrodynamics. And this is really, this is really the core of why we're taking this quantum field theory course. First of all, it gives us lots of interesting and important contacts with experiment, verifications of the theory of quantum electrodynamics. But also, it really tells us a lot of important sort of conceptual information about quantum electrodynamics and more generally about features of quantum field theory. So the things that we'll be encountering today are really going to involve some rather deep lessons for how we think about quantum field theory. Okay. So let me just remind you. So last week, what we did is we computed the one-loop corrections to the propagator of phi to the fourth theory, or maybe it was phi cubed. I guess it was phi cubed theory. And that was really a warm-up to the calculation that we'll be considering this week, which are the loop corrections to a photon propagator in quantum electrodynamics. Okay. And what we'll see is that the loop corrections to the photon propagator in quantum electrodynamics include all sorts of important physical effects that are perhaps things that one could have anticipated, just sort of conceptually, but we'll finally be able to make a little bit more precise. Okay. So what we're interested in doing is calculating the photon-photon two-point function. So represented in terms of Feynman diagrams, you might represent this two-point function like this. So this is an object with two indices that I'll call mu and nu, associated with those two external photons, the two external legs. And the blob in that middle of the Feynman diagram is supposed to represent all possible contributions to this two-point function, computed order by order in perturbation theory. Now, if we want to try and study this perturbation theory systematically, what I'd like to begin by doing is starting to expand this in terms of one-particle irreducible diagrams, as we did last class. So, of course, the leading contribution to this photon-photon two-point function will just be the usual tree-level propagator, which we studied in quite some detail last semester. And then you could start computing loop corrections. So, for example, last time we defined the notion of a one-particle irreducible contribution to a two-point function. So this consists of all possible contributions to the two-point function, which have the property that if you cut one line in that Feynman diagram, you still have a connected diagram. So, for example, things where you just have one tadpole sticking off from the diagram would not count as one-particle irreducible, but things like just one electron running in a loop would be one-particle irreducible. And then you could imagine a contribution where you have two sets of one-particle irreducible diagrams arranged next to each other, and so on and so forth. And if you think about it carefully, if you use the no tadpole result, the statement that all of the tadpoles have to be removed order by order in perturbation theory using the counter term, then all of the contributions to the photon-photon two-point function can be written as either as some number of one-particle irreducible contributions all arranged next to each other in a line. So here, what we'll do is we'll give a name to the one-particle irreducible contribution to the propagator. So I'll call it pi, just as I did in the case of a scalar field. The only difference being that now pi is a tensor. It's a two-index tensor rather than a scalar. And if we wanted to compute it in perturbation theory, the leading contribution would involve an electron loop. Okay, so there's an electron going around in a loop, plus possibly some counter terms, plus various terms that are higher order in the perturbation expansion. And today we're actually going to compute this one particle irreducible diagram that I've drawn for you right here. But before I do so, I want to spend a little bit of time motivating this computation by explaining to you exactly what it is pi mu nu should look like and what sort of physics it should contain. Before I do so, let me just pause and see if there are any questions. Any questions so far? So the important point is that pi mu nu is sometimes referred to as the photon self-energy, or alternately as the vacuum polarization. And the reason why it has this name is that this one particle irreducible contribution pi mu nu really describes modifications of the photon structure due to virtual pairs of electrons and positrons. And in particular, if you think about it, this quantity pi mu nu is really describing the physics of the screening of electrical charge due to the presence of virtual electron-positron pairs as a function, say, of the distance between two charges. So let me just try and make that statement a little bit more precise. So let's imagine that we have two charges. Okay. So this is a charged particle and this is a charged particle. And we want to describe the interactions between these two charged particles. Then at leading order in tree-level quantum electrodynamics, so let's say that those two charged particles on the left and the right are electrons, then you would describe their interaction by studying the exchange of a photon. So you would calculate some sort of Feynman diagram like this. So this might represent 2-to-2 scattering of two electrons off of one another via the interchange of the photon. And when you calculate this diagram, it includes, for example, the physics of the Coulomb interaction between the two electrons. Now, however, once you consider the loop corrections to the propagator, so this diagram would be computed by including the photon propagator between those two electrons. Now, however, we're imagining studying quantum corrections to that, where you have, say, for example, the first quantum correction that I wrote down above. And you can see that effectively what this is doing is it's saying that we modify the interaction between these two electrons that are scattering off of each other by imagining that you can have some sort of virtual E plus E minus pair that's nucleated in between those two electrons, exists for some finite amount of time, and then disappears. Okay. So this term here represents the screening of electric charge due to these virtual electron-positron pairs. And as we'll see, this means that you have some effective reduction in the strength of electromagnetism due to quantum effects. Okay. So naively, you would expect that this would be a reduction of the strength of electromagnetism due to quantum effects. And I should mention, of course, that this is a general phenomenon that one would expect not just in quantum electrodynamics, but let's say that you were in some condensed matter system where you had charged objects moving around through some medium which itself has charged excitations. Then you would expect those charged excitations to screen in some way the charges that are present in your system. And indeed, the way that you would calculate that screening is precisely by doing the calculation that I'm doing for you today. So today I'm doing it in the context of quantum electrodynamics, where you have electrons that have spin 1/2 and have this particular coupling. But in some other sort of medium, say in some condensed matter medium, this is exactly the same calculation you would do. Okay. And so what I'd like to do now is just describe in a little bit more detail exactly what we would expect the answer to look like before actually computing the answer. So what do we expect this tensor pi mu nu to look like? So the first thing to notice is that pi mu nu is a function of the momentum of the so if this is an incoming photon with momentum p, then pi mu nu should be a function of that momentum p. And it should also be a symmetric index 2 tensor. So just by Lorentz invariance, you can quickly convince yourself that there are only 2 possible tensor structures that you can write down involving a momentum p that are symmetric in the 2 indices. And just by Lorentz invariance, you really couldn't say anything, say, about the relative size of the 2 coefficients appearing for those 2 different tensors. However, last semester, we noticed that whenever you have a gauge theory scattering amplitude, gauge invariance implies that if you contract one of the external momenta with that scattering amplitude, then you have to get 0. Okay. That was gauge invariance, essentially because whenever you have an external polarization vector epsilon, you could shift epsilon by adding to it a momentum. That was just a gauge transformation, and it shouldn't change any of the physical answers for scattering amplitudes. So that manifestation of gauge invariance was called a Ward identity. It tells us that the external momentum contracted with the photon self-energy has to be 0. So in particular, that means that pi mu nu must be proportional to a particular linear combination of g mu nu and p mu p nu. Okay. In particular, it has to be proportional to this projection operator, g mu nu minus p mu p nu over p squared, times still some undetermined function that I'll call pi, now without the 2 indices. So the first thing that we should notice is that this tensor appearing here, we could call it delta, is a projection operator. So, for example, that means that if you take delta squared, so delta mu nu, delta nu rho, delta, not covariant derivative, you'll just get a delta back, so delta mu rho. Okay. So that's the basic property of a projection operator, that it squares to itself. So that means that if you go ahead and compute this two-point function, so remember, it takes the form of the free propagator plus the 1 pi contributions plus two 1 pi contributions right next to each other, plus so on and so forth. Then what does that look like? Well, that's given by the free propagator, which I'll just write down in Feynman gauge, so it's g mu nu over p squared. And then you get minus I g mu nu over p squared. Sorry, let's write that as g mu rho over p squared coming from this propagator, a pi rho sigma times I g sigma mu over p squared. So that comes from one pi diagram. Then the terms where you have 2 insertions of pi, 3 insertions of pi, and so forth. We can now use our results using Lorentz invariance and the Ward identity to extract all of the tensor structure from the self-energy pi. What do you get? You get a minus I g mu nu over p squared. That's just the first term. And then you get the second term will be minus I g mu rho. Oops. Okay, something's going on. G mu rho delta rho nu over p squared times pi. And then if you think about it, the 2 pi, 3 pi, and so forth contributions will just give you additional factors of pi squared, pi cubed, and so forth. Okay. So we can then just combine the sum using the fact that 1 plus pi squared plus pi cubed and so forth is just 1 over 1 minus pi. So what this is going to give you is minus I over p squared. Now with the correction term, so that 1 plus pi squared and so forth will resum into 1 minus pi. And then that's going to be multiplied by g mu rho times this projection operator, which we'll write as g mu nu minus p mu p nu over p squared. And then there's a little correction term, which is not going to turn out to be important, which comes from the fact that this original term here didn't have a delta, so I need to add in a little correction term here to turn that into a delta to make this series here start with a 1 plus pi squared and so forth.
Which indices on that pi first line of the
Oh, yes, my apologies. Thank you. Okay. Good. Okay. The important point, however, is that in any calculation, all of the terms here proportional to p mu, p nu are gauge terms. Those are terms that depend on your choice of gauge. So remember that in the arc psi gauge, the propagator was g mu nu plus psi times p mu over p squared. So and gauge invariance was then the statement that all of those that the actual result for any scattering amplitude calculation was independent of the value of psi. So that means that in any computation of a scattering amplitude, the p mu p nu pieces will cancel. That was just gauge invariance. So what that means is that if you want to write down the full corrected propagator at all orders in perturbation theory, in Feynman gauge, all you do is take your free expression for the propagator, which was minus I g mu nu over p squared, and you modify it to include this 1pi correction term. Everything clear so far? And this was just as we found in scalar field theory. When we started calculating the 1pi, the one particle irreducible corrections to the propagator of the scalar field, we found that those 1pi correction terms could essentially be regarded as renormalization, as involving the renormalization of the mass of the scalar field. Similarly here, we see that we have corrections to the photon propagator. And similarly, we're going to interpret these corrections to the photon propagator as quantum corrections to the effective charge of an electron. Now, when we did this computation in phi cubed theory, we saw that pi, the one particle irreducible contribution to the two-point function, was divergent. And this divergence was cured when we rewrote everything in terms of physically observable quantities. And we imposed that condition that we wrote things in terms of physically observable quantities by placing some constraints on pi that required us to balance different counter terms against one another. And the exact same thing is going to happen here. And a crucial ingredient when we studied this propagator in scalar field theory was the decision of how we want to enforce these physical conditions. And in the present case, we're going to enforce the physical conditions by placing some constraints on this function pi. So, in particular, let's just think for a second about how we would physically interpret the answer for the propagator in the limit where p squared goes to 0. So for a photon, in free electrodynamics, the propagator has a pole as p squared goes to 0 with residue 1. And just as for a scalar field, we want to fix our counter terms by demanding that the pole of the propagator remains at p squared equals to 0 and continues to have residue equals to 1. So if, for example, the location of the pole were shifted from p squared equals to 0 to some other value of p squared, that would mean that your photon is no longer massless. Okay? That would mean that your photon had become massive, and that would violate gauge invariance, because it's impossible to write down an interacting theory of a photon that has mass that preserves gauge invariance. So we're going to demand, so first of all, that would demand that pi squared has to be regular, has to be finite as p squared goes to 0, and then its value at p squared goes to 0 would fix the residue of the pole. Okay? So a renormalization condition, if we wanted to write it this way, would just be that pi evaluated at p squared equals 0 has to be set equal to 0. So to keep the location and the residue of the pole at p squared equals to 0, as in free quantum electrodynamics. There was a question?
Yeah, so earlier you said that the p nu piece will cancel out. Is that's fixing pi to be 0, because otherwise I don't see how that's...
Yeah, okay. That's right. So in any physical computation, so this was when we checked the Ward identity, when we checked, for example, In quantum electric, we didn't actually prove it in QED, but last semester we checked that in a variety of different diagrams, all of the p mu terms cancel.
That showed up as gauge invariance.
That was gauge invariance. That was gauge invariance. That was gauge invariance. I mean, one way of seeing this was that depending on your choice of gauge, you can change the coefficient of p mu in the propagator. Okay? So if your theory is gauge invariant, it has to be independent of that choice. Now, we didn't actually prove, so it's possible, it's a little tricky, it's not that bad actually, but it's possible to give just a diagrammatic proof by thinking hard about Feynman diagrams of that fact, but we didn't do it last time, I just stated it as an assertion. And there certainly could be theories where, well, okay, let's not get into that. Good, okay. So the renormalization condition that we want to impose is that pi vanishes as p squared goes to 0. That's the statement that your photon remains massless and is normalized appropriately. So explicitly, just because I think it makes this renormalization procedure a little bit more clear, let's consider what would happen if we let pi at p squared equal to 0 not be 0. Okay. What would that mean? Well, let's just imagine that pi of 0 is not 0. And then imagine computing, say, electron-electron scattering in quantum electrodynamics, say at very low energy. Or you could even imagine computing electron-electron scattering at some fixed value of the energy. Well, you would start by calculating that Feynman diagram. Then you would calculate the one-loop correction to it, plus all of the various other higher loop corrections to it, coming from quantum corrections to the propagator. And what you would get in the limit where you're taking the energy very low, that is to say p to 0, this would be g mu nu over p squared. You would have 2 powers of the electric charge e squared, because you have 2 interaction vertices. And then you would have this factor of 1 minus pi evaluated at p squared equals to 0. Okay. And this is as p squared goes to 0. Okay. So that means that if pi at p squared goes to 0 was not equal to 0, that would just enter into, we could just regard that as part of our definition of the electric charge. In particular, the parameter E that I've been writing down here is the quantity that appears in the Lagrangian, but it may or may not have anything to do with the value of electric charge that you might actually measure in some experiment. So in particular, you could just define the value of the electric charge, or the physical or renormalized value of the electric charge, to be precisely the quantity that's appearing right here where you would have thought the electric charge should appear. Okay. So you define the renormalized value of the electric charge, E renormalized, to be the square root of 1 over 1 minus pi of 0 times E. And here, maybe what I'll do is I'll call that E naught. So E naught is the bare electric charge. That is to say, the parameter that appears in the Lagrangian. And E renormalized is the physical electric charge as defined in terms of the outcome of some scattering experiment. So in this case, I define the renormalized electric charge, the physical electric charge, to be the square root of the coefficient of g mu nu over p squared in the limit where p squared goes to 0 for electron-electron scattering. Now, of course, at leading order, in the limit where the coupling constant E squared is very small, E renormalized is going to be very close to E naught. Well, let's just say that pi of 0 is going to be given by some expansion in E renormalized. And so if we can calculate pi, then we could calculate order by order the relationship between the bare electric charge appearing in the Lagrangian and the renormalized electric charge. So sometimes you might call this factor the square root of 1 minus 1 over pi of 0. You might call that the charge renormalization. In the same way that we had the factor z sub m, which was the mass renormalization, or z sub phi, which was the wave function renormalization last class. So let's call ze is 1 over the square root of 1 minus pi of 0. That would be the charge renormalization. Now, we can take this one step further. So before I go ahead and calculate pi, I want to take this one step further and tell you a little bit more about how we can interpret this function pi. So I've discussed here the definition of the physical electric charge in terms of some low energy process. Let's now consider what would happen if we have some finite energy process. So in some finite energy process, the contribution to the scattering amplitude that you get would be proportional to g mu nu over p squared times E naught squared over 1 minus pi of p squared. Or if you want to write that in terms of the renormalized electric charge, it would be E renormalized squared times 1 minus pi of 0 over 1 minus pi of p squared. So what you see is that the effect of replacing the tree level propagator by the full propagator could be regarded as introducing an effective charge, let's call it E effective squared, that now depends on the momentum scale that's equal to the actual charge, the physical charge, as defined at some particular fiducial value of the energy, in the present case, very low energy, times some function that depends on momentum. So we can see that the effective charge that appears in quantum electrodynamic scattering processes depends on the energy scale p squared. The effective charge is scale dependent. The effective value of the electric charge that you see in some scattering process depends on the energy of the scattering process. At very low energy, the effective value of the electric charge might take one value. It's the one that we call ER. But at very high energy, it might take some different value. And this really can be regarded as the effective screening. If you have a very low energy process, electrons are very far from one another. They'll be screened a lot by virtual electron-positron pairs. But at very high energies, they might not be screened as much. Any questions on that? Yes.
Is this real now too?
Yes, absolutely. I mean, this is one of the most important. So the fact that the coupling constants in your theory are effectively scale dependent is perhaps the most important fact we're going to learn this semester. It's one of the key, important, crucial, wonderful facts about quantum field theory. It's fundamentally an effect in interacting quantum field theory. It's a fundamental effect of adding interactions to quantum field theory that your coupling constants magically, effectively become scale dependent. Questions? Yes?
When P squared is non-zero, you still have gauge invariance, okay?
Correct.
So if you scroll up to when we got rid of the,
Yes.
at some point we got rid of the PUP term,
Yes.
it doesn't look like they cancel immediately when you do that, right?
Okay, good. So, I used the fact that they had to cancel. Okay. I did not prove to you that they do cancel. So what I have not done yet is actually calculate pi mu, pi nu, and tell you that it has the form that we need it to have for gauge invariance. That is what I'm going to do today. It will require me to introduce a different regularization scheme, one that preserves gauge invariance. But so far, I've just told you what properties it should have and given you the physical interpretation. I did that before I did the computation because the computation is long and horrible, and I wanted you to know why we were doing it. But yes, good question. Now, let me just make one other comment here, which is that because pi is formally a small quantity, because it's zero at leading order in perturbation theory, you could also rewrite this at leading order as 1 minus pi of p squared minus pi of 0 plus higher order terms. So effectively what we're going to do, rather than introducing explicit counter terms and then fixing them order by order in our expansion using some regulator, effectively what I'm going to do is just calculate pi of p squared directly for you and then subtract off the term where p squared is equal to 0. That's completely equivalent to enforcing our normalization conditions and demanding, for example, that the pole in the propagator remains at p squared equals to 0 and has residue 1. Okay. So enough motivation. I think I've convinced you that this vacuum polarization pi is an important quantity. So let's go ahead and compute it. And along the way, I'm going to be able to check gauge invariance. Okay. So my first warning to you is that this is a non-trivial calculation, and it'll involve some of the technical tricks that we introduced last week when we computed one-loop diagrams in scalar field theory. But it'll also require me to introduce a few more technical tricks. So if it appears, so I apologize that by necessity, this is going to be a somewhat elaborate computation. Okay, so this is the one-loop diagram that we want to calculate. So what is it? Well, we just use our Feynman rules that we worked out last semester. There's a minus sign because you have a fermion loop. There's I times the coupling constant squared. there is the integral over the undetermined loop momentum. We have a two propagators. You have an I over k squared minus m squared is the first propagator, and an I over k minus p squared minus m squared is the second propagator. And then the numerator involves a trace. So from the first interaction vertex right there, you have a gamma mu. From the second interaction vertex over here, you have a gamma nu. And then in between them, you have the various numerators that appear in the electron propagator. So for the upper propagator, you have k slash minus p slash plus m. And for the lower propagator, you have a k slash plus m. So that's the numerator here. And then we can use our various gamma function identities to simplify this numerator. So this is the sort of calculation that you did last semester when you were calculating tree amplitudes. So for example, we can use our gamma matrix identities. So there was, remember that the trace of any odd number of gamma matrices vanishes, whereas the trace of an even number of gamma matrices does not. So here you have a g mu nu, g rho sigma, minus g mu rho, g nu sigma, plus g mu sigma, g nu rho. That was the trace of 4 of these guys. And the trace of 2 of these guys is just 4g mu nu. So you can then simplify the numerator in this expression, that trace of the product of gamma mu and the various gamma mu times all the various gamma matrix stuff. And what do you get? Well, you get 4, okay, that's the easy part, times, let's see, there's a k mu times k minus p nu, plus the same thing with mu and nu switched, so k nu times k minus p mu. Then there's the final term, which you get by contracting mu with nu, so that gives you a k dotted into k minus p, and then you get an m squared term from the trace of gamma mu nu times m squared. And all that times g mu nu. So that's the numerator. The denominator can be simplified, as we did last time, using Feynman's trick for combining denominators. So 1 over k squared minus m squared times 1 over k minus p squared minus m squared. You introduce a parameter x. It's usually called a Feynman parameter. That's integrated from 0 to 1. And in fact, this is exactly the same integral that we did last time. So I'll just tell you what the answer is, or rather remind you from last time. So you had a k squared minus 2x k dot p plus x p squared minus m squared, all quantity squared. So that's as in last time. And then, as last time, what we want to do is shift the integration variable to complete the squares, so that we define a new momentum that I'll call L, which is k minus x dot p, so that the integral becomes an integral d4L over 2 pi to the 4th times our numerator, I won't bother copying down, divided by L squared minus delta squared, where delta is found just by completing the squares over here. So delta, this is exactly the computation we did last class, is m squared minus x times 1 minus x times p squared. So I haven't done anything fancy here. I've just used some gamma matrix identities. I used Feynman's trick to combine the two denominators into one. And then I shifted the integration variable. And the reason why it's useful to shift the integration variable is that now if I do my Euclidean continuation, so that I take L to L Euclidean, just as we did last class, the integral becomes the integral d4 L Euclidean over 2 pi to the 4th times this numerator divided by L Euclidean squared plus delta squared. And this is now an integral in 4-dimensional Euclidean space that is spherically symmetric. Okay, it's invariant under the 4-dimensional rotations of that Euclidean momentum L. So this is a 4-dimensional Euclidean integral. Okay. Now there's still a couple things that we can do to simplify this integral. Okay. So up above, I wrote the numerator in terms of k. Really what I need to do is rewrite it in terms of L. But in doing so, there's actually a neat trick that I can use, okay, which is that the integral that I'm writing down here, the d for L Euclidean, as well as this denominator here, are all invariant under L goes to minus L. So that means that any term in that numerator, when you rewrite it in terms of L, that's odd in powers of L has to be 0. So I can drop all of the terms in that numerator that are linear in L. So what does that give you? Okay. So the numerator, well, what do you get? Well, you've got those various k nu terms, which are going to give you L mu, L nu. Okay, it's a little too bad that it's not all fitting onto one slide. There it is. Okay. And then from this term here, you have a g mu nu times L squared term. Okay. I'm writing those two terms first for reasons that'll become clear in a second. And then you have no terms that are linear in L. I've written down the two terms that are quadratic in L. So now you have only the terms in the numerator that go like L to the 0. Okay. What are they? Well, you need to take into account the fact that L is k minus xp, so k is L plus xp. So every time you have a k times k minus p, you get an x times 1 minus x times p. So you get a minus 2x, 1 minus x, p mu p nu, coming from these terms up here. And then from that last term, you get plus g mu nu times m squared plus x times 1 minus x p squared. Okay. Any questions on that? Okay. Now, there's another trick that we can use to simplify this integral, which is that if we're ever left with an integral of the form L mu, L nu over some function of L squared, then that has to be a tensor, which is a symmetric 2 tensor. And the only symmetric 2 tensor that you can write down is going to be g mu nu. So if you think about it, that just has to be equal to g mu nu times the integral d4L over 2 pi to the 4th times L squared over f of L, along with a coefficient that's fixed by using the fact that g mu nu, well, by taking the trace of both sides of this equation, by contracting both sides of this equation with g mu nu, since the trace of g mu nu is 4, you just need to put in a factor of 1/4 there. So that's just one more trick that we can use to simplify this integral. And so what you're left with is an expression for pi mu nu, which, well, there was an e squared out front.
Just to make
Yes.
Sure. Is that only true in 4 dimensions? Like the
We'll
Gilbert
understand.
two
Yeah.
tensor in 4D?
The fact that it's the only symmetric 2 tensor that you can write down is true in any D. That factor of 1/4 is special to 4D, as we're going to discover momentarily.
Well, okay, so what's your reason then? Because the reason I was thinking was that in 4D, any vector tensor where it has a symmetric piece and an asymmetric piece, there should be some.
That's true in any
unique-
dimension. That's true in any dimension.
That's right. But then saying there's a unique symmetric tensor, so you're saying that's also true. Every symmetric tensor in dimensions has to be proportional to the
Well, in every symmetric, so let's put it this way. If there are no other vectors around or other tensors out of which you can construct your symmetric 2 tensor, it's the only one you can write down. So for example, the fact that the denominator here depends on delta, which is a scalar, means that you can't construct it out of the vector p mu, because delta only depends on p squared. If this denominator here were more complicated and it depended on the vector p mu, then there could be another term allowed by Lorentz invariance, which would be p mu p mu. But it only depends on a scalar quantity, namely p squared and m squared. And so the only thing you can write down is g mu nu. Another way, for example, I just also used the fact that the integral d4L of L mu over any function of L squared had to be 0. I argued it by using L to minus L symmetry. I also could have argued it by using the fact that there's no Lorentz invariant vector.
Were you saying that the numerator has to have the same functional dependency of the denominator?
So, sorry.
Yeah, so why could the numerator not depend on some vector quantities that were relevant to the problem, even if...
Well, okay. If you stare at this integral, there's no vector that appears in that integral. Delta is a scalar. That's the important point. So the problem, of course, has a vector in it, but that integral does not.
Yeah, so as long as all the vectors are contracted within...
That's right.
the
That's correct. Right. Good. Yeah. Okay, so that means that if we have this integral for pi, you get something like there was an integral dx from 0 to 1, and then an integral d4L over 2 pi L to the 4th. Oh, and then you have various different terms. So the first term, you get a minus 1/2 g mu nu times L squared. And then you have a bunch of other terms. You had, what was it, a minus 2 x times 1 minus x, p mu p nu, plus g mu nu, m squared plus x times 1 minus x p squared. All over L squared plus delta, where delta is given by m squared minus x times 1 minus x p squared. Okay. So the first thing to notice is that this is a divergent integral, just as we found last week when we considered the propagator in phi cubed theory. Last week, however, we had a logarithmically divergent integral. And if you just stare at this integral and you study for example, the naive regulator, where you just cut off the integral at some momentum and then take that momentum away, this is a more divergent integral. In fact, it's quadratically divergent instead of logarithmically divergent. So if, for example, you tried to regulate this integral using a hard cutoff, that is to say, by integrating only over momenta less than some scale lambda, and then taking lambda to infinity, then this first term here, involving an L squared, will lead to a contribution to pi mu nu, so you get an integral d4L times L squared over something in the denominator that goes like L to the fourth. So that will be quadratically divergent. Okay. And then there'll be various other terms that go like log lambda. And those other terms will involve g mu nu and p mu p nu. So there's something extremely unsatisfying about this result if we use the hard cutoff regulator. And the problem is that this answer violates gauge invariance. So this regulator violates gauge invariance. Or I should say breaks gauge invariance. In particular, I argued for you that the Ward identity said that pi mu nu had to be proportional to g mu nu minus p mu over p squared. And you can see that the leading divergence in this hard cutoff regulator scheme actually does not have that form. So that's not necessarily a problem. It just means that if you use this hard cutoff, the intermediate steps in this problem would involve terms that are not gauge invariant. They would have to cancel out all at the end of the day, but it means that the intermediate steps of the calculation are going to be more complicated. Remember, the rule in physics is always to try and enforce all of your symmetries at the intermediate steps of your calculation in order to make the calculation as simple as possible. And this is actually a more general lesson. Okay. So in general, it may be possible for different regularization schemes may preserve different symmetries. So for example, we already know that the hard cutoff regulator breaks Lorentz invariance, okay, because it introduces its other energy scale. And we now see that it also breaks gauge invariance. So what we would really like is a regulator that preserves gauge invariance. Now, in fact, the Pauli-Villars regulator that we used last time, actually, if you're careful, you can introduce that and preserve gauge invariance. But in fact, what I want to do is use what's a technically much simpler regulator and one that will apply in all of the problems that we're going to be studying later on in the semester, which is dimensional regularization, or DIMREG for short. So dimensional regularization is a much less intuitive way of regulating these apparently divergent integrals. But it has the advantage that in some ways it's much slicker and it gives you much simpler results. It's a little counterintuitive. So one of the problem sets that you have due on Friday is a quick little calculation with DIMREG just to show you exactly what its relationship with other regulators is. But it is, once you get used to it, a much, much faster way of doing calculations. So the basic observation of dimensional regularization is the fact that if you consider the integral that we're trying to do, so it's the integral d4 L Euclidean of 1 over L Euclidean squared plus delta quantity squared, and you consider that integral not in 4 dimensions, but in d dimensions, this integral will converge whenever d is less than 4. So the idea of dimensional regularization, which is actually kind of ridiculous, but just ridiculous enough to be useful, is that we should treat the dimension d as a continuous parameter. And then compute this integral as a function of the continuous parameter d, and take d to 4 at the end of the calculation. So for example, i.e., if you write d as 4 minus epsilon, then epsilon is a regulator, just like the cutoff scale lambda if you had some hard cutoff, or in Pauli-Villars. And all of our integrals will diverge as epsilon goes to 0. So in fact, epsilon can be regarded as a cutoff parameter, just like the dimensionful cutoff parameter lambda in Pauli-Villars or in the hard cutoff method. Now, we're not actually imagining that our field theory is in 3.9 dimensions or 4.1 dimensions or something like that. There are actually people who try and do that, but we're not going to try and do that. What we're really doing is just using this as a calculational trick to get to control the divergences in these integrals in a systematic way. Really, sort of the granddaddy of all renormalization schemes is the derivative method that we introduced last time, where you, for example, you just take the number of derivatives of this self-energy in order to get a finite answer, and then you integrate it back up using the physical conditions as boundary conditions to fix the constants of integration when you do that integral. That, I think, is the renormalization scheme that I want you to have in your head whenever you're using DimReg or Pauli-Villars or something like that. But DimReg is just a sort of slick set of tricks that we can use to reproduce the answers from that result. Okay? So for example, in the problem set that you're going to do for Friday, you're going to do a simple example of dimensional regularization for an integral and verify that it gives you the exact same answer as you would using a different cutoff scheme. Okay. And then it's a straightforward mathematical exercise to go ahead and implement this to regulate our various integrals. So let me just give you an example of that. Okay. So for example, the integral, one of the integrals that we need to do is an integral of 1 over L Euclidean squared plus delta quantity squared. Okay, that's the integral that's logarithmically divergent, that gave us the terms proportional to p mu, p nu, for example, in our photon self-energy. Okay. So this is a straightforward integral to compute. I don't think I'm going to do it for you because life is too interesting for me to compute integrals in class. It might not be so interesting that you can't compute them on your problem set. I haven't actually decided. Maybe I'll make you compute them on the problem set. It's not so bad. So let me just write down the answer for you. Okay. So for example, if you look in the appendix of the textbook, there are all sorts of expressions for these various integrals. So this is the answer that I've for this d-dimensional integral of 1 over L Euclidean plus delta quantity squared. It involves a gamma function. One of the things that you need to remember about the gamma function is that as the argument of a gamma function is taken to 0, the gamma function diverges. It has a simple pole, looks like 1 over x, along with a constant term, typically called gamma, which is, I forget what it's called, the Euler-Macaroni constant or something like that. Euler-Macaroni constant. I always just call it the Euler-Macaroni constant. So this gamma function has a pole as its argument goes to 0, so that this integral, as you take d to 4, so let's set d to be 4 minus epsilon, this integral has a simple pole as epsilon goes to 0, coming from the gamma function. So what do you get? You get a 1 over 4 pi squared. And then, well, I'll write down the answer for you and then explain it for a little bit. You get a 2 over epsilon minus log delta. And then you get a bunch of constants, which are very rarely actually important because they usually are just cancel out in the counter terms, plus various terms that are of order epsilon, so vanish as you take the regulator away. So that pole, the 2 over epsilon, comes from the fact that gamma of d2 minus d over 2 is gamma of epsilon of 2 that has a pole that goes like 2 over epsilon as epsilon goes to 0. That log delta term actually is a little subtle, so it's worth explaining. So if you just stare at this expression right here, so you get that's gamma of 2 minus d over 2, otherwise known as gamma of epsilon of 2, times delta to the d minus 2, d over 2 minus 2, which is delta to the minus 2 epsilon. Okay. You might think that as epsilon goes to 0, that gives you a delta to the 0, so it's independent of delta. But you need to be a little bit careful when you do that. Okay. The reason being that you can write this as, what is that? That's 2 over epsilon minus gamma plus order epsilon. And then delta to the minus 2 epsilon is e to the minus 2 epsilon log delta, otherwise known as 1 minus 2 epsilon log delta plus higher order in delta. And so this gives you a 2 over epsilon minus gamma minus 4 log delta plus higher order terms. Okay, and I see I got the factor of 2 wrong here. That's epsilon over 2. They are supposed to cancel. Okay, good. Right. So the point is that even though naively delta to the minus epsilon over 2 goes to 1, as epsilon goes to 0, there's a pole coming from the 1 over epsilon, and you have to be careful to cancel them. This often happens when you do these regularization schemes. You need to be careful to keep all of the terms, or else you might get something wrong. There's one final comment that I'll make about this answer, which is sort of important, which is that delta in this expression is a dimensionful quantity. And it doesn't actually make sense to take the log of a dimensionful quantity. So you might actually wonder what's going on here. How is it that I'm taking a log of a dimensionful quantity? the point is that this parameter epsilon should really be regarded as the log of the cutoff scale. So for example, if you took this integral that I've written down for you right here, and you regulated it using, say, some hard cutoff, then what you would find is that epsilon goes like the log of the cutoff scale, where the cutoff scale is dimensionful. And so what you're really getting here is not a log of delta, but a log of delta divided by the cutoff scale squared. In fact, that's something that you'll prove on the problem set Friday, due Friday. That epsilon goes like the log of the dimensionful cutoff scale. And it all combines together to give you something nice and dimensionless, a log of delta over that cutoff scale. Okay, and that is to fix the dimensions in log delta. Okay. Now, what I want to do then is prove to you that when we compute our photon self-energy using dimensional regularization, you get an answer that is perfectly consistent with gauge invariance and Lorentz invariance. In order to do so, we're going to need to be a little bit more careful about how we treat the various terms that arise when we use dimensional regularization. So I want you to remember that our integral involved various terms that, at least naively, depend on the space-time dimension. For example, it involved the metric, it involved the various gamma matrices, and so forth. Now, if we study the theory in d dimensions, then you need to use the fact that the properties of the metric and the gamma matrices and so forth depend on what dimension you're in. So, for example, the trace of the metric is equal to d rather than 4 in d dimensions. So that means that in our integrands, we replaced L mu nu by 1/4 g mu nu times L squared. In d dimensions, that has to be 1 over d times g mu nu times L squared. So that's one correction. In fact, that's going to be a crucial correction, which is going to restore, which is going to cancel that quadratically divergent term that we found using the hard cutoff method. But more generally, when manipulating these gamma matrices, one should, in principle, be careful about various terms that depend on the dimension. So it turns out, and this is not something that's going to be important for the present calculation, but is something that may be important in the future, is that when you use dimensional regularization, we can still treat the gamma matrices as 4x4 matrices, but there are now d of them rather than 4. So, for example, that means that gamma mu, gamma nu, gamma mu is now not 2 gamma mu, but gets a correction term. And there are various other sorts of corrections to these gamma matrix contraction identities that all basically follow from the fact that g mu nu contracted with itself is now not equal to 4, so a gamma mu contracted with a gamma mu should now be equal to d rather than 4. But we always preserve the Clifford algebra that the commutator of gamma mu with gamma nu is just proportional to the metric. questions before I continue? So I have about a little more than 10, okay, I can almost finish the photon self-energy contract. Is it okay if I go about 5 or 10 minutes over today, just so that I can finish the photon self-energy calculation? I'll go into deficit spending. I'll let you go 5 minutes early next time. Okay, so let's go ahead and compute the photon self-energy in dimensional regularization. So let's first just consider that leading term, the one that gave us the quadratic divergence. So what did that look like? Well, that was an integral d4L over 2 pi to the 4th times, what was it? It was 2 L mu L nu minus G mu nu L squared over, what was it? In Lorentzian signature it was L squared minus delta squared, or in Euclidean squared it was L Euclidean squared plus delta squared. Now in dimensional regularization, we replace that by the integral d dl over 2 pi to the d. And then L mu nu is going to be 1 over d times L squared G mu nu. So we get a 2 over d minus 1 times L squared over L squared minus delta quantity squared. And then, again, it's a straightforward exercise to actually just compute this integral. So the integral, so what do you get? You get 2 over delta minus 1 times G mu nu times the integral of d dl times L squared over L squared minus delta quantity squared. That integral, I'm just going to tell you what the answer is. You could go ahead and look it up in your textbook, or maybe you'll compute it next week. I haven't decided yet. Well, you get a 4 pi over d, 1 over 4 pi to the d over 2, a d over 2, a gamma of 1 minus d over 2, a gamma of 2, which is just 1, right? Gamma of 2 is 1. Okay, 1. And a delta to the d over 2 minus 1. Now, the important term here, so this is that integral. Okay. The important term I want you to pay attention to is that gamma of 1 minus d over 2. The important point is that gamma of 1 minus d over 2 diverges when d is equal to 2, 4, 6, etc. But it's because the function gamma of x has a simple pole at x equals to 0, minus 1, minus 2, and so forth. And it's the fact that that integral of L squared over L squared minus delta squared diverges when the dimension d is equal to 2, that reflects the fact that this is a quadratically divergent integral. The quadratic divergence means the fact that this integral would diverge even in d is equal to 2. But the point is that even though that gamma function diverges when d is equal to 2, this coefficient out front vanishes when d is equal to 2. And it cancels that divergence. So you can then go ahead and rewrite this integral. So let's multiply that d over 2 through. So d over 2 times this function, that guy there. So d over 2 times 2 over d minus 1 is otherwise known as 1 minus 2 over d. And 1 minus 2 over d times gamma of 1 minus 2 over d is otherwise known as gamma of 2 minus 2 over d. So what is that? That's a 1 over 4 pi to the d over 2 times a gamma of 2 minus 2 over d minus d over 2. Then you have a delta of d minus 2 d over 2 minus 1, which I'm going to write as delta of d over 2 minus 1. Sorry, I'm going to write that as delta of d over 2 minus 2 times delta. Okay, because all of the other terms that we're going to find in the integral go like gamma of d over 2 minus 2 rather than gamma of d over 2 minus 1. So this means that we can then go ahead and put it all together. Oh, well, the first thing I want to mention is that this, once we do this cancellation, this only diverges as d goes to 4, not d goes to 2, which means that the quadratic divergence has disappeared in dimensional regularization. So that's probably worth commenting on. So the quadratic divergence disappears. And that's a signal that dimensional regularization is consistent with gauge invariance. So, of course, to show that dimensional regularization is consistent with gauge invariance, we don't just need that quadratically divergent term to cancel. We need to compute pi mu nu and show that it's proportional to g mu nu minus p mu p nu over p squared. So let's go ahead and do that. I promise you that we're almost done. So we can then just go ahead and put it all together. To go ahead and compute pi mu nu. So what do we get? Well, we had an e squared. Okay, that's the easy part. We have, so what do we have? Let's just remind ourselves of our formula for pi mu nu. Okay, here it was. So we had that e squared out front. We had an integral dx from 0 to 1. And then we need to regulate this integral. Okay. So this first term here, that dangerously quadratically divergent term, is the one that I just did. And now we just need to compute these other terms here. Okay. Those can be computed using this formula here. Okay. So let me just write down the answer for you. The thing that you want to remember is that there was a 1 over 4 pi to the d over 2, a gamma of 2 minus d over 2, and a delta of d over 2 minus 2. So we get a 1 over 4 pi squared. Okay. Then we get an integral dx from 0 to 1. We had a gamma of 2 minus d over 2 divided by delta to the 2 minus d over 2. And then we had various different terms. Okay. So from this term here, we had a delta g mu nu. And then we had two other terms, okay, which are, let's just write them down, which are these terms right here. We had one proportional to g mu nu and one proportional to p mu p nu. So let me just write those, copy those down for you. We have a g mu nu times m squared plus x to the times 1 minus x p squared, and a p mu nu times x times 1 minus x. And delta here is equal to x times 1 minus xp squared minus m squared. Good. Now, if I've done everything correctly, this is where the magic happens. This is supposed to be proportional to g mu nu plus p mu p nu, or g mu nu minus p mu p nu. And in particular, that requires that this m squared term cancels. And you can see that it precisely cancels in front of this term, from this term. And you can also see that I dropped a factor of 2. When I copied this down, there's a factor of 2 right here. Okay. And that factor of 2 is crucial, okay, because there's this term which combines with this term to give you an answer, okay, which, let me write it like this, which is proportional to G mu nu minus P mu P nu over P squared. So I wrote that. So I'll write it as G mu nu minus P mu P nu over P squared times that function that I called pi, where pi of P squared is equal to E squared over 4 pi squared, sorry, E squared over 4 pi squared, times the integral dx of x times 1 minus x times, well, this quantity right here, okay, which we can then take epsilon to 0, d to 4. So what is that? Well, that's the same calculation we did earlier. So as epsilon goes to 0, you get the pole 2 over epsilon. You get a couple of constant terms. And then you get an important log delta term. Sorry, with a minus sign. Plus terms that vanish as you take epsilon to 0. So this is the photon self-energy. And it's important, of course, to remember that this log delta term comes because naively that term delta, that term goes to 1 as d goes to 4. But there was a pole coming from here that cancels against the first linear term as epsilon goes to 0 that gave you that log delta piece. This is just as we did a little bit earlier. So the first thing that we should be proud of is that we get an answer consistent with the Ward identity, consistent with gauge invariance. So the answer is consistent with gauge invariance. And as expected, pi has a divergence. Pi is naively divergent. The photon self-energy is naively divergent. But when we impose our physical renormalization conditions, that is to say, when we write everything in terms of the physical renormalized electric charge, in terms of the bare electric charge, you're going to get a finite quantity. And of course, that is just equivalent to subtracting off the value of pi at p squared equals to 0, which gives you the answer, e squared over 4 pi times the integral from 0 to 1 dx, x times 1 minus x. And we get, so what was delta? Delta was x times 1 minus xp squared minus m squared. So we get log of m squared over m squared minus x times 1 minus x p squared. So this then is the finite contribution to the photon self-energy when we impose our physical renormalization condition, that we write everything in terms of the physical renormalized electric charge instead of the bare electric charge. This is a completely finite quantity. There's no divergences anywhere. It's a function of p, which reflects the fact that the electric charge is effectively a function of the scale at which you probe the system. And next class, what we're going to do is spend some time studying the physics of this answer. So for example, this answer contains within it the quantum corrections to Coulomb's law, okay, due to the screening of electric charge. This leads to the Lamb shift in the spectrum of the hydrogen atom, or part of the Lamb shift in the spectrum of the hydrogen atom, among other things. So this is indeed one of the more important things that one can compute in quantum field theory. Sorry for going over for a few minutes. I just figured I wanted to finish the calculation while we were going. Let me just stop here unless there are any questions. So if there are things that were a little bit unclear or where I went a little too fast in the calculation, don't worry. Sure, I'll find ways of making you do calculations like this on problem sets. And we'll spend some time next class just sort of physically thinking about and understanding this answer. Question?
So we're working with pi of p squared minus pi of 0 because we took 1 minus pi 0 over 1 minus pi of p squared.
Yeah.
And we expanded in small.
I mean, that was at leading order. Really, we should be talking about 1 minus pi of 0 over 1 minus pi of p squared.
Okay, and then you said, okay, but we're not going to work with this. We're going to replace this with 1 over 1 minus.
If it makes you feel,
blah, blah, blah.
if it makes you feel a little better, we could have done this a slightly different way, and we could have introduced a counter term like I did last term, and then demanded that that counter term was fixed by setting pi of p squared equal to 0, pi of 0 equal to 0. That would be a completely equivalent way of doing this. Is that not
I guess
okay?
It seems a little sketchy to me because we're expanding in small pi, where pi is already infinite, right?
No, but this is exactly as we did last class. Remember that when you introduce counter terms, they are divergent, but they're formally higher order in perturbation theory. This is what a counter term does for a living. Yeah. I mean, if all of this nonsense with counter terms makes you unhappy, then you could always go back and just work only in terms of physical quantities from the very beginning. And then you would never get any divergences anywhere in any of your problems. But the intermediate steps of your calculation would be a little bit more complicated. So remember, like when we studied, what was it, phi-4 theory? Okay, was it phi-4 theory? When we studied phi-4 theory and considered the one-loop correction to the lambda phi to the 4 coupling, that's exactly what we did. We just rewrote everything in terms of a physical coupling. And indeed, starting, maybe next class and going into next week, we're going to study in more detail the corrections to the electron vertex in QED. And that will lead us to the anomalous magnetic moment of the electron. Okay? And it'll be a very similar sort of calculation. Okay, maybe I should stop here because I'm over time. Sorry again for going over time. And I will see you on Thursday.